Yes. So let's start with your second lecture on special values on zeta functions.
Okay, thank you. Share my screen. Seems to work. Okay, so let me just summarize briefly yesterday's talk. X always has the same meaning, a regular connected scheme of dimension D, proper over Z. It could be a variety over a finite field. So this entire picture that I'm going to describe will work in that case. But for simplicity, I assume it's in characteristic 0. We have a zeta function. We want to describe the vanishing order and the leading coefficient. And we do this using a modification of étale motivic cohomology, where motivic cohomology is defined in terms of higher Chow groups. So Bloch defined the cyclic complex, the key property being that mod L for a prime that's invertible, it's the root of unity sheaf, and then rationally it recovers the Adams eigenspace of K-theory. So we have these assumptions entering into our construction. We assume that motivic cohomology is finitely generated in low degrees, which is the hardest and which is basically the only assumption needed in characteristic P. We have the Beilinson regulator on the level of complexes. That's all well defined. This pairing is well defined, but its perfectness is an assumption. So that's what I call the Beilinson conjectures, and it reduces to the usual Beilinson conjectures. And then we have art individuality with finite coefficients, which is known in many more cases. So all three assumptions are known if X is spec F for a number field F. At least in this case, there's no assumptions. And this is the situation I want to talk about first. But let me say in general first, the way the zeta function is described is via these Weil-Arakelov complexes. Again, they are constructed using the assumptions from étale motivic cohomology by certain mapping fiber constructions using art individuality and the Beilinson conjectures. And so you have groups with Zn, Rn, and R mod Z coefficients. They have these properties that the R coefficients have trivial Euler characteristic, and the R mod Z coefficients are compact Lie groups, so they look like a torus across a finite group. And then the way the zeta function is described, the secondary Euler characteristics, the vanishing order, and the volume of the compact groups is the leading coefficient. And to define a volume form, we use this derived de Rham complex with some correction factor. Of course, if you put a correction factor, the statement is vacuous, but we assume this correction factor to be 1 in many cases, except it's not. And so that was the status of the conjecture for a long time. And then after a while, we realized what this factor should be. And it actually leads to another integral complex, which gives the L value on the nose. So I will explain this TC plus first today. But let me first talk about spec OF. So what happens for spec OF? Of course, the zeta function is a Dedekind zeta function. All assumptions are known. Finite generation is known by Borel's result. These motivic cohomology groups are essentially algebraic K groups up to 2 primary part. So, for example, K3 of Z differs from H1 Z2. The conjecture on the vanishing order reduces to Borel's result for all integers n. So let me try to rewrite our conjecture as a class number formula. So it has these 2 versions already. The one I just gave using compact volumes or using a fundamental line. And there's a third way to write it, simply in the style of the class number formula. So concretely, you would take the Beilinson regulator, which maps into this R space here, product over the infinite places, and you have this simple real space here. And once you tensor the motivic cohomology with R, it's an isomorphism. Except for n equals 1, you have to take the sum zero space, just like is well known for the unit regulator. Okay, so this is basically the Bailenson conjectures are true in that case. And there's clear analogs of the class number roots of unity and regulator for higher n. So the even k groups, they're always finite. And so their cardinality is an analog of the class number in higher weight, Hn. Then the torsion in the odd k groups is the analog of the roots of unity, and the rank of the k groups is given by the regulator. And its co-kernel has a volume once we choose another Z structure in the target, and we just choose the obvious Z structure in this target Deligne cohomology group. So we get clear analogs of the usual quantities in the class number formula. And so if we make our conjecture explicit, it just looks like a class number formula. So for non-positive integers, it's just this product h1 minus n times r1 minus n over w1 minus n. And if you remember the class number formula where n is 0, that's exactly how it looks. It's much simpler for negative integers than at the positive ones. So at the positive integers, we have a non-vanishing L value, so the leading coefficient is the value. And again, the formula amounts to this. So there's a certain power of 2, a certain power of 2 pi, h, n, r, and w, n. Exactly like the class number formula, except the additive terms are a little bit more complicated. So we have this power of the discriminant, and we have this correction factor. So this was the correction factor appearing in our formulation here, which we could compute to be this factorial rigorously for abelian fields, but we expect it to be this factorial for all number fields. So we just have to put it into this formula without any further explanation at this point. And again, this class number formula holds true for n equals 0 and 1 because it's the traditional one. But for arbitrary n, it's only true for abelian fields because one can prove our conjecture using the Tamagawa number conjecture. So the question is, how do we explain these additive terms? Do we just write them out, which would be fine enough, but do they have any further significance? And that's where cyclic homology comes in. So this derived de Rham cohomology I was talking about before yesterday, which was defined initially by Illuzy, it has a different definition, or it occurs in a different context, namely as a graded piece on cyclic homology. So that's a story in algebra that started with Kohn and some Russians, Feigin Tsigan, in the early 80s, and then Lotte Quillen wrote about it. And it's often called additive K-theory because K-theory is somehow related to the group homology of GLN, and cyclic homology is related to Lie algebra homology of the Lie algebra of GLN. But in any case, it has a direct definition using Hochschild homology, which is a classical construction. So for any base ring K and any algebra K or A over K, one has the concept of Hochschild homology. It's this derived tensor product. Something like a self-intersection of the diagonal in A tensor A, if you think of this geometrically, but in a derived sense. So all tensor products are derived. And this is a complex of abelian groups, but with a ring structure, you can view it as a simplicial ring. And it also has a circle action in a homotopical sense. So the action on the homology groups is trivial, but not the action on the entire complex. So it has a circle action, an action of S1, And the homotopy co-invariance of this circle action is one way to define cyclic homology. And so HC is an additive analog of K-theory and is an analog of the motivic filtration on cyclic homology. So that was defined some years ago by Antio, but the corresponding spectral sequence was already discovered in the 90s by Matthias, and but he didn't frame it in terms of a motivic filtration. So yeah, so this uses Bailenson T structure and filtered complex in various constructions, but in any case, it's fairly explicit using the definition of cyclic homology. And what's interesting that the graded pieces of this motivic filtration just give back exactly this derived Aram homology that I was talking about before, going back to Illusie. So this is an additive analog of the motivic filtration. This graded pieces is motivic homology, but in the Zariski topology, not the étale one considered here. And how does this play out for spec OF? So let's go back to this easy example. So what's the additive K-theory of spec OF? So this derived Aram complex you can compute just basically from Illusie's definition and some theorems. So it's a two-term complex that has OF in degree 0, and then a certain differential to a finite abelian group of cardinality, the discriminant to the power n-1. So if n is 1 for the classical class number formula, it's just OF. It's like the tangent space of the multiplicative group. But for higher n, it's this two-term complex. For example, if n is 2, this is really just the Kähler differentials of OF, but not in general. And so by this spectral sequence from the previous slide, it turns out that cyclic homology in 2 consecutive degrees is just given by the cohomology of this two-term complex. So in other words, the motivic filtration is an easy filtration. It's just given by the double speed Postnikov filtration in that case, because OF has a small dimension. So so that's just a name. I call this the additive K group, but it's the cyclic homology group, or the derived. In this case, we don't need to derive because OF is flat over Z. So it looks like that. And then from this, what I just said, it's clear that you could interpret this term appearing in the class number formula down here, this denominator, as some kind of product of an additive class number with an additive regulator, where the additive class number is the cardinality of the even additive K group, or, well, yeah, which is H2n-3. There's a shift. And the co-volume of the obvious regulator on the additive group to the infinite places, this co-volume is just the square root of a discriminant times the index of this odd additive K group inside OF. So we don't know what these groups exactly are, right? But from this description, we know that the additive regulator and the additive class group have to multiply to this quantity there. So that gives an interpretation where these terms in the class number formula come from, partially because it doesn't account for this correction factor. So so there was still this factorial here. So we've only accounted for these terms. And it was discovered by Morin again, because he had the confidence that there should be an exact formula. I didn't actually believe there's an exact formula, but he found one. So to explain this factorial, one can do something that's very fashionable nowadays. So instead of taking the base ring K to be Z, one can take the base ring to be the sphere spectrum. So, so all this higher algebra has been made accessible by Lurie's work and goes back to the 80s to Waldhaus and Böckstedt. They had this basic idea that one can do all this algebra over the sphere spectrum, which is some kind of ring, but only up to homotopy. And so there's an analog of Hochschild homology, which is called topological Hochschild homology. And there's lots of activity currently on these theories. But the reason we found it interesting is if you take the obvious analog of cyclic homology, which we call TC plus of X, which is the homotopic coinvariance of the circle action on this, then we can compute it and a factorial will show up. And the reason it shows up is because by this theorem of Madsen-Lindenstrauss from 2000 computing THH, there is this factor J here in odd degrees 2J minus 1. So if you would compute ordinary Hochschild homology of OF, it would be the same answer, but without the J. And for topological Hochschild homology, you get this factor J. And so you look at the spectral sequence for this homotopic coinvariance. So that is just a group homology of S1 acting on the homotopic groups. And this can be easily analyzed, and you find, lo and behold, that again, TC plus 2m minus 3 is finite, and TC plus 2m minus 2 is a sublattice in OF. But now these quantities add up exactly to this whole factor that appears in the class number formula. So, so we can write down a very clean formula, which is now having this additive class number and the additive regulator in the denominator. But we can also make this product explicit and just write down this factor. And so that kind of suggests, and then other reasons also suggest that this TC plus theory is really the correct one. So I call it TC plus and not TC because the notation TC is already occupied. So there's a notion of topological cyclic homology that people have defined, and that is actually something different. It's all a bit confusing, but so this is the obvious analog of cyclic homology. Okay, so that's kind of the starting point. It's just Morin discovered this in the basic case spec OF, and then of course the question is this more general? Is TC plus the right theory? And so we have to find a motivic filtration. So in case of spec OF, the motivic filtration is again essentially the Postnikov filtration. So we have the weight n groups in 2 consecutive degrees nicely organized. But in general, it's certainly not, just like for K groups. And so Morin was able to construct this filtration using the constructions of Bad, Morrow, Scholze and combining it with Antio's work before. And so, so one gets a motivic filtration. One defines the graded piece to be this R gamma L omega X over the sphere spectrum. So I want to point out this does not have an independent definition. So there's nothing like a Kähler differentials over the sphere spectrum, or maybe there is, but we don't know any definition. It's just defined by the left-hand side as this graded piece in analogy to this theorem here. So the left-hand side defines the right-hand side. And it's kind of obvious to call it something like a Durham homology over the sphere spectrum, but I don't know if there's an independent definition. And so the main fact about this graded piece on TC plus is that it actually differs from the derived Durham homology exactly by our correction factor that we had guessed before, and that is the right one for spec OF. And it's also the right one for other reasons that I will talk about later, having to do with the functional equation. Yeah, so that's the story. And then recently in work of Bhatt and Lurie on prismatic homology, they also defined a motivic filtration independently, I think. They're probably the same. Okay, so that's the story on TC plus. Maybe if there's any questions, we could have a little break here. If not, I move on to my other main topics for today. So compatibility with BSD is one topic, and compatibility with the functional equation I want to talk about. Yeah, so it would be interesting to compute these groups. So again, we only know the product of the class number and the regulator. And very often also for the usual class number and regulator, it's easier to prove properties about the product and it's harder to separate them. And so even for the integers Z, I'm not sure TC plus has been computed. It should be doable, but I'm not sure it has been done. Would be kind of nice if there's any structure to these groups, or maybe not. Okay, compatibility with BSD. So this is now one dimension higher. So the general case for D equals 2, starting out with such an X, then the structural morphism to spec Z has what's called a Stein factorization. So it factors over spec F for a unique number field F, which is just a constant field in the function field of the curve, right? So, so that means push forward with the structure sheaf is just OS, and then on the generic fiber, one gets a nice smooth projective geometrically connected curve over a number field F. So that's the basic geometric situation for dimension 2. And I want to compute our conjecture to BSD. So BSD doesn't concern all of the curve, it only concerns the H1 part. So we have to disassemble our conjecture into the HI parts. Luckily for a curve, it's not so hard to do this. And part of our philosophy was to not to pass to some motivic decomposition, but to get a potentially easier picture. But here we're just forced to do it. But now we're not over a field, we're over spec F. So S is always this space spec F. And if you think about the analogous situation where S would be a curve over a finite field, and you talk about analytic sheaves, you might have heard that there's a T structure on analytic sheaves called the Perverse T structure, which would mirror properties of the unknown motivic T structure that one expects on DM. And so similarly here, when I decompose my X into H0, H1, H2, I mean this in the sense of this nebulous conjectural motivic T structure. And so again, the H0 and the H2 part are simple. So the H0 is just a motive Q0, so to speak, but over spec F. So its zeta function is the Dedekind zeta function. The motive H2 is a Q minus 1. So its zeta function is the shifted Dedekind zeta function. And the interesting part is this zeta of H1. So how does this look like? The interesting part. So it depends on the bad fibers of the arithmetic surface. And so for each finite place, one has this nice family of curves, the arithmetic surface. So over each finite place, you get a curve, but it might not be irreducible. So CV is the set of irreducible components of the fiber. Kappa V is the finite residual field. And then each component has itself a constant field. So capital F was the constant field of the entire surface, but each component might have a different constant field from the residual field. And I call RVI its degree. And then this zeta function of the H1 is essentially the Hasse-Weil function of the Jacobian, which is the L function of the H1 on the generic fiber. Right, that's the usual formula that I discussed in my talk on motivic L function. So it would be the H1 of the generic fiber. But then you have this finitely many Euler factors reflecting the bad fibers. So yeah, it's written down here. So if there's only one irreducible component, for example, if the fiber is smooth at this point, then the degree has to be 1 because the fibers are all geometrically connected. If it wasn't 1, then the fiber wouldn't be geometrically connected. Only if there are several components, some of them might have a larger constant field. And so if there's only 1, these two factors cancel out and I don't get any contribution. So I only get contribution from fibers that have more than one component. So it's very simple actually. And yeah, and so we're interested in BSD, so we want to describe the zeta function at n equals 1. And that means we also have to decompose our motivic complex, V1, which describes n equals 1, somehow into its H0, H1, and H2 part. So this is just a push forward now in the étale topology of GM that we need to look at. And so we need to define a motivic complex associated to this H1 motive. Again, there is no rigorous category DM with the T structure, so our motivic complex will just be constructed ad hoc as a complex of étale sheaves on S. So this situation has actually been studied in an old paper of Grothendieck on the Brouwer group. So he proved that the higher derived images of GM under this map F is here our structural map, that they're all 0 in higher degrees. And the R1 is what he called the relative pK functor, which are called P. So it's just the sheafification of the pK group of X sheafified over étale schemes on the base S. And so one gets a truncation triangle just from derived functor here. So the F star of GM is again GM because of our assumption here. We took the Stein factorization, so the push forward of OX is OS. And then the third term in the triangle is our P here, that R1. And so that splits off the H0 part of our F star GM, right? This GM is the H0 part of our F star GM. And to split off the H2 part, we look at the degree map from P to the integers. So in every fiber, we get somehow a line bundle, and the line bundle on the curve has a degree because all the fibers are curves. And so you can define a degree map on this sheaf. And the kernel, I mean, in the sense of the derived category, so that's our complex P0, which represents the relative H1 motive. On the generic fiber, P0 is just represented by the Jacobian, okay? As an étale sheaf on the generic fiber. Okay, so this splits off the H2 part, which is a Z, right? Because remember, the H0 was kind of a Q, but then we twist by 1, so we get a Q1, and then we get a Q0 in degree 2. Okay, so we work with this complex P0, and we do all our Weil-Arakelov modifications that are kept under the rug to this complex P0 on the base S, and we get Weil-Arakelov groups, and we get our conjecture in this case. And so here's the main compatibility theorem. Fairly straightforward. So the vanishing order part are equivalent. So the BSD has the statement that the vanishing order is the rank of the group of rational points of the Jacobian. And our statement is the analogous one where we have to take pick 0 of the integral model. And the ranks might not be the same. They differ exactly by these classes of the irreducible components, right? I mean, if you think of pick as a divisor class group, they give you classes in pick 0. And so these ranks might be different, but these identities are equivalent. And then for the leading coefficients, again, our conjecture has 3 equivalent formulations, right? As I was already indicating, also in this case, there's a formulation in terms of the fundamental line. The tangent space in this case is just this single group. because the H0 corresponds to the H0 part, and the H2 part has no tangent space, so it's just the H1, XOX. Yeah, the derived Durham complex reduces to OX because we're in weight 1. And then there's an equivalent way of stating our conjecture using volumes of certain compact groups. So there's a complex R gamma C Weil-Arakelov with P0 tensor R mod Z coefficients, and it has two cohomology groups which are both compact, and one could write down how they look like. And there's a volume form coming from the tangent space, and you can write our conjecture as this kind of volume statement, as I did before in the general case. And then you can write it in the style of a class number formula, and it looks like this mess here. So there's a certain group, which is analogous to the Tejchafarevich group, the Brouwer group of X bar, which I'm going to explain. But this factor delta squared also belongs to this cardinality. So this is somehow the cardinality of the H1 part of the Brouwer group. You have a certain period, and you have a certain regulator. I will explain all these terms on the next slides, and this formula is equivalent to this formula, which is BSD, the standard formulation. So the way this is proven is just very much by hand comparing these two expressions directly. So we don't use any fancy other formulation, we just use BSD and compare it to this explicit formula. And so that means we have kind of three things to do. We have to compare cardinality of SHA to this Brouwer group times delta squared. We have to compare the two periods and compare the two regulators. And so let me explain this on the next slide. So the interesting part is, of course, SHA and the Brouwer group. So this is a long story historically. How do you compare SHA of the Jacobian to the Brouwer group of the arithmetic surface? That involves some interesting arithmetic of the arithmetic surface. Namely, you have these indices. So what is the index of a curve? Let's look at globally. So you take the generic fiber curve over a number field, and you take the co-kernel of the degree map. So what does that mean? If you think of PIC as a divisor class group, and it's generated by closed points, by the classes of closed points, but the degree map is the degree of the closed point over the base field F. So if there's no rational point on the curve, this co-kernel of the degree map is exactly the GCD of the degrees of all residue fields. Right? So this is what's called the index of a curve. So if there's a rational point, this is 1. In fact, if there's a rational point, all of these quantities are 1 here. And so they're only subtle if our curve has no rational point. And so delta V is the analogous local index. Then there's also what people call a local period, where you don't take PIC, but you should take the sheafified PIC, which I call P. And then there's also this co-kernel of the map of PIC 0 XF, which is just the usual group of divisor classes, but kernel of the degree map. This maps to the Jacobian, but again, the Jacobian is the sheafified version. And this might not be an isomorphism, might have a co-kernel, might not be the same. Okay, so it's known that the period and the index differ by 1 or 2, so they're either equal or differ by a factor of 2. Okay, so if the Brouwer group is finite, or equivalently if SHA is finite, so finiteness of these two groups is equivalent, then we have this formula here. So this was attempted by many people, but it was first completely proven by Geiser. But Geiser still had the condition that the number field F is totally imaginary, and then I proved it for all number fields. And if the number field has real places, one has to replace the Brouwer group by this Brouwer group of X bar, which is the kernel of the map to the real places. And so again, this factor delta squared appears here because in our computation, it's really this cardinality, which is the cardinality of a suitable H1 part of the Brouwer group. So there's a certain, if we make on this complex P0 the Wegetal modifications, the H1 of this complex will have this cardinality here on the left-hand side. And that's why I'm putting the delta square on the left-hand side. And you can also see that this right-hand side is not always a square, or this factor here is not always a square. If delta V prime is not equal to delta V, that's reflected by the fact that the order of Chow is not always a square. That was discovered by Poon and Stoll, some paper around 2000. But the cardinality of this Barrow group is always a square because it has an alternating pairing if it's finite. So even the two primary part is a square. Just a little advertisement that this point of view of arithmetic schemes is a bit more elegant than the Tetschaff-Ravitch group. Okay, so that can be proven, but it's complicated, especially if there's real places. It uses duality results of Shuji Saito from the late 80s on GM on such an arithmetic surface. Okay, so that's one input in the formula. And then comparing the two regulators, so one has the regulator of the Néron-Tate-Hyde pairing on the Jacobian, and then there's the Arakelov intersection pairing on the arithmetic surface. And so if one compares the two regulators combined with the torsion part, which one has to throw in, so I divide out pic 0 of OF because it belongs to the H0 motive and not to the H1 motive. And so one gets this formula. And to prove it, it's complicated again, but it can be done using results of Bosch and Liu on component groups of Néron models. So the component group will show up in this regulator computation. And this part here is just the leading coefficient of our remaining Euler factors that I was writing down here. So if you take the leading coefficient at s equal 1, you just get this here. But it also comes from the Arakelov intersection pairing. So that compares the two regulators. And then to compare the two periods. So on the one hand, we have a period that only depends on the generic fiber via the Néron model of the Jacobian, right? That this doesn't see the arithmetic scheme X, it only sees the generic fiber. So it's basically a Betti-Durand period or Deligne period on these two situations. And one can show that they're actually equal, I mean, up to sign. So, so these two groups are clearly equal. I mean, the H1 of a curve is the H1 of the Jacobian. This only depends on the generic fiber. But then the right-hand side, the Durand part, this depends on the actual arithmetic surface X. But nonetheless, the two periods are equal. For example, this can have torsion, this H1, right? Can have torsion, whereas the Lie algebra is always torsion-free because J is smooth. But the periods are the same. And use, again, results which are conveniently already in the literature, which just fit what we need here to compare these two. By the way, when I say we, this is due to a student of myself, Daniel Siebel, and myself mostly. Okay, so we can compare all the quantities in the explicit BSD formulas and everything cancels out and you get that they're equivalent, which is quite reassuring. So even two primary parts came out correct, which was really a surprise that our definitions worked out in that case. So now we have equivalence of our conjecture with BSD. Of course, we can leverage this to prove cases because people have proven cases of BSD. The most traditional one goes back to Rubin, because the M-elliptic curves of rank 0. So basically, one has this class of CM elliptic which are defined over F, so that F adjoint the torsion over CM is abelian, is an abelian extension. So that's the class curves going back to Shimura. And Rubin in the early 1990s basically proved the BSD formula in this case up to a few primes, like basically the two primary part and some other primes. And he also proved finiteness of Chow a little bit before. So these were the first cases where one had non-trivial results towards BSD. And so in recent work with Ashay, we completed this, and now BSD is complete if the L value is non-vanishing. This. And then there are some rank 1 cases. I mean, this is probably not the most up-to-date version. I mean, the result from 2015 by Liu and Tian, an infinite family of rank 1 curves where one can prove that both the rank and the vanishing order is 1. And the full BSD formula holds true in that case. And so that means now, because all the assumptions in our conjecture are satisfied, I mean, these finite generation assumptions just boil down to finiteness of Shah, or equivalently the power group. And so, so now if we take a genus 1 curve, which is a torsor for such an E, then its Jacobian is E again. And so we can take any regular model of such an X, and then our conjecture will be true by the previous theorem. So at least we have some evidence. So this is again a CM curve, but maybe nowadays one can prove infinite families of non-CM rank 1 curves where BSD is complete. I don't know. So there's lots of progress in this direction. Okay, so for the remaining time, I want to talk about compatibility with the functional equation, unless there's questions on this. Okay, so let's go back to the general picture. Again, X is regular, proper flat. Dimension D is important because that appears in the functional equation. And first one has to complete the zeta function with infinite factors. And these are exactly the same factors that occurred in the talk on motivic L functions, because everything only depends on the generic fiber at infinity. In other words, on the Hodge structure, on Betty cohomology, if I take the complex points. Remember, X of C is some nice, compact, complex manifold, possibly disconnected, depending on the constant field. And so it has a Hodge structure, and already by Sayre in the late 60s was given this recipe of associating an L factor to a Hodge structure, because every Hodge structure is a direct sum of simple ones, and for simple ones one has this easy list with these gamma functions. So one has to complete this function infinity, and then the main statement is so we have a conjectured functional equation for the completed zeta function. It involves this conductor associated to X called the Bloch conductor. So it was first defined by Bloch around the early 1980s, and it's basically a measure of de Morgan in the de Rham complex. So remember, if X were smooth over spec Z, then the de Rham complex would coincide with the derived de Rham complex, and it would consist of locally free terms. The differentials would be locally free by smoothness. But of course, there's not many interesting examples which are smooth. I mean, there's the projective line over Z, for example. But all interesting examples are not smooth, they're just regular. And then you will have torsion in the de Rham complex, and the Bloch conductor measures this in some way. For example, if X is spec OF, the Bloch conductor is the absolute value of the discriminant, which indeed is what occurs in the functional equation of Deligne zeta function, where D is 1. Okay, so if we assume the functional equation, and again, for higher dimensional X, this is proven whenever one has connection to automorphic L functions, and one has identified the Bloch conductor with the Artin conductor appearing in automorphic L functions. So there's an interesting additional problem. The Artin conductor is a completely different construction using the L-adic representations and the ramification. But for surfaces, it's known to be equal to the Bloch conductor by a result of Bloch. And in some higher dimensional cases, I think semi-stable X by Kato-Sato. So, and then the identification to automorphic L functions will prove this functional equation in many cases. Okay, and then what I'm saying here is that our special value conjecture is also compatible. So in other words, our statement at n, remember the L value spans this integral fundamental line, is equivalent to the value conjecture at d minus n for any n in Z. Again, special value spans the fundamental line at d minus. And this is a great advertisement for our picture. So remember, this fundamental line now contains, as I was indicating, it contains the this graded piece of TC plus, right? So, which I call the Ram cohomology, derived the Ram over the sphere spectrum, which amounts to having the correction factor being equal to this factorial. So that's what's in our fundamental line delta. And the fact that these two are equivalent goes beyond the framework of the Tamagawa number conjecture. So this is not known for TNC, even for speco F. If F has complicated ramification, the corresponding volume computations using the exponential map, Bloch-Kato exponential map, are not done yet. And this compatibility is not known. But for our conjecture, it works out nicely. So how do we prove this? So of course, there is a comparison needed between the two fundamental lines, which involves sort of an infinite fundamental line, kind of accounting for the quotient of the two Euler factors at n and d minus n. So philosophically, this is a quotient of the Euler factor at n divided by a factor at d minus n. And if you sort out the terms in the fundamental line, you end up that this comparison term here involves those spaces here. Again, you have derived the Ram at n and d minus n, and you have this Betty part in R gamma c at n and d minus n. And so what's happening basically is that rationally, this is just the Betty plus space, and this will be the Betty minus space. So they combine to the full Betty cohomology. But you have to also use duality on the d minus n part. And again, in the de Ram, you have to use duality on the d minus n part. And then the two pieces will combine to the full algebraic de Ram cohomology. And the trivialization of this psi infinity amounts to the period isomorphism between Betty and de Ram. So that's rationally, that's a classical story going back to Deligne when he made his period conjecture. In the critical case, he also proved compatibility with the functional equation, and at least the transcendental part involved here is just the Betty-de Ram comparison isomorphism after one has applied duality to these d minus n parts. Okay, so there's a period which I call X infinity, which is again in this same formalism. It spans the integral fundamental line under this period isomorphism. And yeah, as I was saying, so this is a certain Z lattice in the Betty plus space. And so so what do we have to do now? So we have to closely look at this comparison isomorphism at infinity. So again, just repeating what I just said. So you have to use Poincare duality on the generic fiber at infinity, but X of C has dimension d minus 1. So Poincare duality has top degree d minus 1, which means here occurs actually an n minus 1. And then you have the plus space, and then you combine the Rn plus the Rn minus 1 into a C. Of course, they sum up to, remember, this is just 2 pi I to the n times R inside C, right? That's what this means here. And so these two sum up to C. If you take the plus space, you get, by the Betty-de Ram comparison isomorphism, the plus space in de Ram, which is the real de Ram, which is again the integral to Ram tensor R with this truncation. I can truncate less than D because as far as ranks are concerned, this derived Ram coincides with the Ram, and since X has dimension D minus 1 generically, then it only has a rank up to omega D minus 1. So in higher degrees, this L omega is torsion. So if I tensor with R, it all disappears. And I just get usual de Ram. So I can truncate by D here. Don't have to take the full de Ram. And then by this truncated by D can be pieced together from truncated by N and the dual of truncated by D minus N by some isomorphism. Okay, so that's an elaborate explanation of this psi infinity. And so we have our period. Basically, the period relates this lattice here to this lattice. Right, these were the terms in our infinite fundamental line. That's the X infinity. And we have to relate it to the quotients of the two infinite Euler factors, right? That's what appears in the functional equation. So the quotient and some power of the conductor, which also appears. And since I'm using derived de Ram and not de Ram over the sphere spectrum, I have to put in my correction factor, which was this bunch of factorials. And lo and behold, these factorials exactly give the factorials in the gamma function. So if you have any knowledge of the gamma function, gamma of n is n minus 1 factorial. And so these factorials in our C infinity exactly cancel out with the factorials in the gamma function. And what's left is a certain power of 2 and a certain power of 2 pi and a certain power of the conductor. And what we need to show is that these products are equal to X infinity. So we have 3 steps concerning those 3 powers here. And the power of 2 to the D plus minus D minus, I'm not going to explain the exact terms, but this is a complicated computation that was done by Morin using Verdier duality on this space. Remember, this X infinity is some plus space, so that means geometrically it's actually the quotient space of the complex points by the complex conjugation. And yeah, and it's actually quite a lengthy computation. And he did that using our definitions, and we didn't know what to expect first, if the factor comes out right, but it did. So if you put these two together, you get the Betti cohomology times our factor that we need, that occurs already in this right-hand side. Now that you've computed in terms of integral Betti cohomology, you have the Betti de Ram comparison isomorphism. And both of these, both Betti and de Ram, satisfy a duality integrally, and you have to compare Poincare duality on both sides. For Betti, I mean, for even with Z coefficients, there's Poincare duality on this manifold, right? And there's also duality here. And comparing those, you get this factor here, which is a correct power of 2 pi plus some power of the conductor. And and then finally, you need to use duality on the D minus n side to get the fill n on derived de Ram, and then combine the derived de Ram modulo fill n, which is this, times the fill n to the total derived de Ram. And in that process, you pick up another power of the conductor. And these two powers of the conductor exactly amount to this power of the conductor, which with the square root here, the d over 2. The square root occurs from the fact that we use Poincare duality, so that means it's like a quadratic form on this space, right? So and then we have to take a square root to get the period back. I mean, it's it's not so easy to explain without going into more details. Okay, and And so this result of Takeshi Saito was actually what initially gave us confidence that we could prove compatibility with the functional equation. So so remember, we have this derived de Rham complex, which, like the usual de Rham complex, you can imagine made out of exterior powers of the differentials or the cotangent complex in the derived setting. And so what Takeshi Saito proved is a duality for the derived exterior powers of the cotangent complex. And so that result kind of was our first input, how this could be used to prove compatibility. And it turned out to be a crucial ingredient. So what's this theorem? So now we're talking about derived exterior powers of the cotangent complex, but the cotangent complex is just concentrated in degree 0. It agrees with the Kähler differentials in that case, except the differentials might have torsion because the thing is not smooth over Z. But it's still just not a complex, it's a single group in degree 0. But the derived exterior powers are a somehow obscure operation. Only on the generic fiber they coincide with usual exterior powers. But it was already looked at by Saito and also Kato in their proof of Bloch's formula. And all this material led Saito to prove this duality. So this is now just about coherent sheaves, right? So omega is a coherent sheaf. The derived exterior powers are also coherent sheaves. So this is the usual Grothendieck duality for coherent sheaves on this proper scheme X. This, so you have a comparison map between derived de Rham exterior power R and exterior power d minus 1 minus r, which is sort of the dual degree on the generic fiber. And this is the dualizing complex on X, which is a certain line bundle because X is a local complete intersection over Z. And if you had a perfect duality, this would be an isomorphism. But it's not. It's only an isomorphism on the generic fiber, where the thing is smooth over Q. And in general, if on the part where it's smooth. So you have some co-kernel, which is concentrated in the bad fibers. It's a torsion, a coherent sheaf. And so its cohomology will be finite because X is proper. And Saito's formula says that its multiplicative Euler characteristic is just given by the Bloch conductor, which is very nice. And so using this result, we leverage this from exterior powers of cotangent complex to the derived de Rham complex, and we get this formula here. Yeah, that's already the last slide. So I guess I'll stop here.
Thank you very much for your last talk in your mini course.
Thank you.
Questions in the audience, or I can't see the chat, maybe you yourself can have a look there. There's nothing.
Yeah,
so,
just a vague question. Like your this zeta function conjectures, like, does it suggest some for usual Iwasawa theoretic framework is more in the setting of motivic L, starting with motivic L functions, and
yes,
your conjecture suggests that there might be some other framework? Or
yes, I mean it's purely Archimedean. It doesn't use, I mean usually what one does is one takes the L-adic completion of all these motivic complexes, and then one can relate everything to Galois cohomology or Bloch-Kato F cohomology and things like that. And that's exactly what we were trying to avoid. So we're not trying to use Iwasawa theory, which would mean to pass to L-adic coefficients somewhere. But we're trying to make a global picture for whatever it's worth. But that's the goal of the program.
But for example, like as maybe like if varieties happen to vary in some families, like these, your cohomology groups might also vary systematically.
Yes, yes, that's right. Which would basically mean we're talking about motives over some base. I mean, I'm already viewing the arithmetic scheme X somehow as a family over spec OF. That point of view is certainly helpful for all of this. So I have a family with characteristic P fibers for all P. But yeah, but using, I mean, the Vasava theory, the Bloch-Kato framework is much more general. If you think about the conjecture of Fukaya and Kato, they basically have a Tamagawa number conjecture for any L-adic family, right? So I have no connection to that. I mean, our picture is not in that generality. No. And also, there is no equivariant L function so far, right? I mean, you might have noticed I only talk about the zeta function, which is completely non-equivariant. So in the case of spec OF, I could talk about the Rt and L functions. And there should be a way of doing that in our picture, but we want to stick with the complete zeta function first for as much as possible.
Thanks.
Yeah. So I have another question. Yesterday you mentioned that the compatibility with your setting with the Tamagawa number conjectures. Now you proved the functional equation property in your new setting.
Yes.
Although, it's not known in the Tamagawa number setting.
Right.
So is there any of your result towards the Tamagawa number settings then, or do the terms cancel out as you considered the total motive somehow?
No, they not necessarily cancel out. For example, if you take spec OF, there's no difference between our setting and the Tamagawa number setting.
Right.
And even for spec OF, it's a hard problem to show compatibility, right? As you probably know.
Sure.
Right. And so we don't have to add anything yet to this hard problem, but at least the idea of using TC plus gives us something to aim for. So whereas in these usual volume computations for Bloch-Kato, one took the usual integers in the tangent space and tried to compare that to the Galois cohomology with ZP n coefficients, right? I mean, one tried to compute the factor between these two lattices under the Bloch-Kato exponential map. And what our picture suggests, one shouldn't take OF, one should take TC plus. And comparing TC plus to motivic homology, which is what people call TC, and that this might be possible. Yeah. So our picture suggests to actually compare two different things rather than what one usually compares.
But this still would decompose into local components or not? I mean,
if I take spec OF, there is no motivic decomposition, but I have an L primary computation for every prime L, so the coefficients somehow decompose, right?
I see.
I mean, if I look at the L primary part, of course, the hard part will be the local fields of residue characteristic L. Yeah, but the starting point would be to take all the coefficient primes and do it prime by prime. Yeah.
But I still didn't get it. So just formally, your functional equation property does not imply anything to the Tamagawa number setting?
Oh, why is that? So let me go back to my slide. Why doesn't it imply anything? So when I was saying compatibility with T and C, here, I was putting this quotient here into the conjecture. So we expect this quotient to be 1. So in other words, the factor C that makes everything compatible with T and C should be equal to our factorial term. And this is the hard part that one still needs to prove. So in other words, does the Bloch-Kato exponential map really map the lattice TC plus to the integral periodically completed motivic homology, which is what people call TC in that case, or the motivic weight-graded piece of TC, the symptomic homology.
Yeah, okay, that makes it clear. Thanks a lot.
Oh, thank you. I could clarify that. Yeah, okay.
Are there further questions or comments? If not, let's thank again Matthias for this very nice mini course.
Thank you, and good luck with the conference. I have to go to bed. It's too late for me now. So.